So what we've done so far actually generalizes to a little bit more than what we've talked about. We've only talked about second order linear homogeneous differential equations with constant coefficients, but this actually extends to any order, as long as the roots of the characteristic equation are distinct. So I'm going to write a degree n characteristic equation. I'm not going to write the initial differential equation because it won't be easy to see from the characteristic equation what the differential equation is. But let's say the characteristic equation factors this way. You get it factored somehow. There are ways to factor. One, there's websites that will factor for you, but also there's ways to factor by hand things that are higher than quadratic. Synthetic division is probably the best one if the roots are rational. We can talk about that in class one day if we have time. But it's a technique from Algebra 2, which maybe was a long time ago. So if it factors this way and you have a1 through an are distinct, distinct is just a fancy word for all different in math, then you have a general solution. And like I said, it's really hard to go from this form actually back to the differential equation, but certainly you would start with the differential equation. It would just be like really long products and sums of these a's as all the coefficients. So that's why I'm not writing it. But the solution to whatever differential equation that is, in general, is you just take all the roots and you put them next to t in the power of e, and you can have arbitrary constants in front, e to the a2t plus a3 to the a3t, and so on, all the way up to an to the ant. So we did this with n equals 2. You can have higher values of n, and then if there are complex roots, and you need to come up with a strictly real solution, use Euler's formula, like we did in the previous day's lectures. And then these complex roots should show up in conjugate pairs. They always will. That's a theorem, again, from Algebra 2, actually. In conjugate pairs, remember the complex conjugate of a plus bi is a minus bi. That means if you have some root a plus bi, then a minus bi is always also going to be a root to that polynomial if the polynomial had real coefficients to begin with. Okay, so this is useful maybe if you have higher degree differential equations, but actually what's kind of cool is this includes degree 1. So if you have some differential equation y prime minus ay equals 0, you know how to do this with separation of variables, but also we can do it this way. We can write the characteristic equation is r minus a equals 0. So a is a root, a is the only root, so that means the general solution is a e to the at. And now you can solve this differential equation without doing any of the work that you were doing before.